our crew patch. This was Monday morning, the 18th of October, as we left our crew quarters there at the Kennedy Space Center. This was the third time we did this. We headed out to the pad. On our way out, we see this scene of the vehicle. I thought it would be good to share it with you because it gives us a lot of inspiration prior to getting on the vehicle. We launched at 10:53 in the morning. The main engine started running. The rocket boosters lifted us off. And again, as I watch this scene every time I watch it, and you have to live this program to know what I'm going to say, I really think nothing but the highest of all the people who make this happen. The people at the Kennedy Space Center who get this vehicle ready. And of course, here as I see the solid rocket boosters, the people at Thiokol who build these boosters, they do a great job. This is a complex machine, and it performed fantastically on this flight. And of course, we'll see booster separation here, and then the three main engines in the external tank that provides the propellant to those engines. The people at Rocketdyne, the 2,500 people who build those engines, who build the complex pumps, etc. The people at Martin who build that external tank. Boy, they do a great job, and this hardware really performed for us. In 8.5 minutes, as you well know, you've accelerated to 17,500 miles per hour. And there we are, and we're in orbit. We open the payload bay doors, and there you see the space lab. In the payload bay, our microgravity research laboratory, and I'll hand it over to Ray.
It takes a couple of hours to get our laboratory up and running so that we can turn it into a mini space station. It takes us very little time to get used to working in zero gravity. As you can see, Dave became quite comfortable with that. We had 14 experiments to bring up and get them up and running for this 14-day flight. One set of experiments that we did were the vestibular experiments, looking at how the inner ear functions with all the other body sensors to give you information about balance, position, and movement. John has a bungee harness on that you can see accelerates him towards the floor when the handle up above him releases, looking at the reflexes that go down the spine. Marty here is doing a pointing experiment. He closes his eyes, then he has to remember where the target is, has to know where his arm is, and how to point his arm at the target. And pointing accuracy seems to diminish in weightlessness. Shannon is making inputs into an experiment that we called Principal Investigator in a Box. The investigator, Larry Young, who's here with us today, put some of the information about assessing the performance of this rotating dome experiment into a computer to help us. John is the subject on this experiment that looks at how dependent you become on your eyes when you no longer have gravity to let your inner ear know where up and down is. You look into a dome that rotates, and we looked at the movement of the eye as it tries to keep the visual field upright. John also made inputs into how much he felt like he was rotating by turning a joystick. The rotating chair experiment looks at how the eye movements react to rotating this way in weightlessness. Again, there's no gravity vector up there, so the sensation of rotation changes. And you'll see that we stop the rotation. Dave pitches his head forward, trying to look at whether the sensation of rotation changes with the plane of your head, or whether this movement makes the sense of rotation stop, as it frequently does here on the ground. Another suite of experiments that we did were the metabolic experiments. In the hatchway there, you see the urine monitoring system, and Dave is holding the urinal that we use in space in his hand. He's injecting some fluid into it to calibrate the urine monitoring system. We collected all our urine on this flight. The urine monitoring system measures the amount and takes a sample of each void so we can bring it back for analysis to see what components were coming out in our urine. Shannon is putting some samples into the saliva collection kit. There are various components in your body that can be measured through saliva. It's a non-invasive way of getting information about different levels of hormones and chemicals in the blood in a fairly easy way. It was another way that we gathered information about the human body. One of the main ways, of course, that we measure components of the blood is to take blood itself. Again, these experiments were looking at fluid and electrolyte balance. We were looking at such things as calcium and protein metabolism, looking at the red blood cells and how they change. There's a problem with the loss of red blood cells in space, looking at all the dynamics, the hormones that control all of these various components of the human body. And we drew blood multiple times in flight and, of course, had them drawn before and after the flight. Bill is putting some of the blood samples into our centrifuge. We have to separate the cells in the blood from the fluid component of the blood, preserve some of the chemicals within the blood, and so they're spun this way, and then the blood is put in a freezer and brought back for analysis here on the ground. It would have been nice in space if we could have done each experiment individually, but frequently we had many going on at the same time. Marty has an accelerometer on his head looking at head movements. Dave is having blood drawn from his arm, and he's also performing the echocardiograph experiment, all at the same time.
When we do echocardiography, it's a part of a suite of cardiovascular experiments. Here you see a two-dimensional real-time image of the heart, the two atrium on the bottom and two ventricles in the top of the picture. We can see the volume of the heart chambers, the pumping dynamics. There I'm holding the ultrasound transducer, which operates similar to radar, to emit and receive sound signals to image the heart so that we can get a full analysis of the central blood pumping action. On the left bottom you see Rick with some instrumentation, a plethysmograph on his leg, which measures the elasticity of the veins and vessels in his leg, also the blood flow in his leg and the size of his leg, which is related to the fluid content. So we integrate the knowledge from the vascular components in the legs with the heart to get a cause and effect relation. Here Bill is doing pulmonary experiments, which when combined with a gas analysis mass spectrometer allows us to understand very accurately the pulmonary function, which also is unmasked by microgravity. The basic physiology is unmasked. Here, an ergometer allows varying workloads to be placed on our body, in this case all the way up to 100%. We obtain a steady state by looking at mass spec outputs of CO2 and oxygen consumption and production, and we can measure how efficiently our body is able to deliver oxygen to its tissues. Here we measure the maximum, absolute maximum ability of our cardiovascular system to deliver oxygen. The combined experiments done together can give us a cause and effect, which is a great strength of this particular mission.
Every day, each of us got up in the morning and we went in and we weighed ourselves. And we weighed ourselves in this device that you see right here, which determines the mass by the number of oscillations that take place. This is slightly different than the scale that you have in your bathroom where you might weigh yourself every day. In addition to weighing ourselves, we also weighed the 48 rats that we had on board. And we used this device, which is on the same principle as the large mass measurement device. We put the rat in, and that's not a rat that I put in there, that is a calibration device, and would measure the mass of the animal to see whether it was increasing or decreasing by the number of oscillations that the instrument had when we turned it on. In addition to weighing the rats, every day we had to check them to make sure that they were eating and were drinking properly. Here you see Marty pulling the feeder tapes out to determine how much food had been eaten in the previous 24 hours by the rats. We did this on every cage, and in every cage there are 2 rats, one in the front and one in the back. And in addition to determining how much food that they were eating, we would check to make sure that their activity level was appropriate and that they were doing okay. And one reason that we had to determine how much food that they were eating, in addition to just making sure that they were doing okay, is that there were a series of experiments in which they were eating labeled calcium, and then we were collecting the feces and determining how much calcium was going in and how much calcium was coming out so they could do a calcium balance. Here you see Bill taking a large bag of water that he filled up from the galley. He's bringing it back to the rat cages so we could fill them up with water. We had to do this about midway through the flight. And this is the first time that this unit had been used, and it worked quite well. Bill and Ray here were able to fill the cages up with water.
This is the General Purpose Workstation, or GPWS, which is essentially a form of laboratory hood that was used to contain particulate matter and any toxic chemicals that might be inadvertently released while working with the rats during the hematology and dissection experiments. And you can see here that I'm deploying a variety of little boxes that contain the numerous pieces of equipment that were required for those hematology and dissection experiments. The folks at Ames Research Center spent an awful lot of time putting together these kits, and we sure appreciated it. We used Velcro and double sticky tape to retain a number of the small items, and you can well imagine that trying to perform laboratory experiments in zero-G would require a different mechanism of restraint and organization than on the ground. Here, Ray is removing a cage from the research animal holding facility into this essentially a cloth sock, which is part of the general purpose transfer unit that's used to transfer that cage across the cabin volume and to the GPWS. And in this way, the rodents were kept isolated from the cabin air volume so that fecal matter or feed particulates could not be released. This is a good opportunity to see what the cage looks like. It's essentially a long drawer. You can see there are two screened panels, each one representing a separate cage for an individual rat. And you can see that it's quite a nice little mechanism for containing both the animals and the feed and the feces trays and the automatic watering system that plugged into the animal holding facility. On this particular day, we were performing some hematologic experiments in exactly the same way that they were performed on us as human subjects. Catheters were inserted into the rat's tail veins, blood samples were collected, isotopic tracers were injected into the rats, and blood samples were again collected in order to determine iron kinetics and red blood cell production rates in the rats in just the same way that were performed on us, the humans. We had a very unique opportunity in performing the dissection experiments on the rodents, in that we were able to collect bone marrow and spleen and thymus, which are the blood-forming organs, in order to study the progenitor cells for those blood cells in their organ of origin, in addition to a variety of other tissues which were sent around the world to a number of research scientists. Here I'm making a pneumethylene blue stained blood film, and this particular stain is for immature red blood cells in the circulation, which then gave us a complete picture of the release of those red blood cells from the blood-forming organs and their development into mature erythrocytes. Ray is working with some microhematocrit centrifuge tubes from which we determined packed cell volume, and as well kept those blood samples for later analysis for iron-binding proteins in the blood. While Ray and I performed some of the hematology activities, Shannon and Dave did most of those, and Ray and I did most of the dissection work. And so we had 4 people working in that hood quite a bit, and you can see that we're all different sizes. And I'm very happy to report from a human factors standpoint that the GPWS functioned very well. We were very happy with the placement of the arm ports. We had sized to our specifications. And as you look at it, it looks pretty much like it does on the ground when we're working in it. You can see how comfortable we were spending a number of hours working in this particular facility.
The next sequence of scenes will show many of the flight deck and mid-deck activities we performed. Here John is flying the in-flight simulation of the landing task. It's a refresher type trainer that we evaluated, flew it for the first time on this flight. It will continue to undergo evaluation over the next several flights to help the crew, particularly in these longer duration missions, in performing the landing task and staying current. Both John and I flew this, and then John and Bill and I performed the entire flight activities from all the way around the hack and down to landing as a crew to work crew coordination. Here I'm just working with the autopilot to perform an orbital test we did. It was an orbital acceleration research experiment, basically an attempt to characterize the on-orbit drag that's on the vehicle. And that's what the vehicle is doing during that test roll about the plus x-axis of the vehicle, part of the calibration for the accelerometers. Earth observations on this flight, we had a real bonanza because of great weather and great viewing opportunities, a long mission, and a good orbital inclination. This is a wide-angle view of the southwest United States with the Grand Canyon in the foreground, progressing up towards the Mojave Desert, and you can see the San Andreas Fault and Los Angeles on the other side of it and the entire Southern California coast. Just about 3 minutes later on a pass such as this over the United States, you might change lenses and do some work with the cameras, then you're ready to take another gorgeous shot of the front range of the Colorado Rockies. Colorado Springs is on the left. Denver will be coming into view shortly here on the right. There it is. And then on the left, that snow-covered peak is Pikes Peak. And then a few minutes after that to New York City. This is a view centered on Manhattan Island with Central Park in the center. We have some New Yorkers here, I can tell. This Earth OBS imagery is used by geologists, meteorologists, ecologists, and a number of Earth and planetary scientists use this for scientific data. This is just a microbial air sampler device, which also coincidentally illustrates some interesting principles of physics here. It has a fan in it that turns, and from the torque effect, it starts the entire device turning in 0G, and then as I tap it, it starts to precess gyroscopically. John is performing some force push-offs here with a force gauge, and with the suite of very sensitive accelerometers we have on the vehicle, we're able to determine some structural dynamics and doing some studies for future microgravity research flights. They can measure accelerations on the order of a millionth of a G.
As has been mentioned, this is the longest shuttle flight ever, and for that reason, John impressed upon us the importance of housekeeping. Here you see Rick taking a vacuum cleaner, and well, we don't have any carpet to clean, but he did use it to clean off the filters to keep our electronics working. We had to work hard to contain all our garbage, and here you see John compacting garbage and then putting it down underneath the floor of the middeck, and we had 2 compartments under the middeck where we stowed all our wet trash. We also had a lot of opportunities to participate in the Shuttle amateur radio experiment. And using the Shuttle amateur radio experiment, we contacted 19 secondary schools around the world. One school in France had their conversations relayed throughout that country, and over 10,000 students either listened or participated in the experiment. In addition, we contacted thousands of amateur operators throughout the world, and we think we really got the word out about how exciting science can be. We also felt it was important to take care of ourselves physically. Here you see John riding a stationary bicycle, and as you can see, he found it very relaxing, as did we all. We also had a series of experiments under the Extended Duration Orbiter Medical Project to see how well prepared we are at the end of 14 days. Here Rick was doing glucometry to measure the glucose level, which Rick, Ray, and I did over 4 separate days. Rick was the operator, and I was a subject on another extended duration orbiter experiment, and this was the lower body negative pressure device. And here you can see me in the bag and Rick making sure that I'm staying healthy and comfortable and keeping the experiment progressing. The concept here is to draw a negative pressure on your lower body to pull bodily fluids back from your head and upper body into the legs so that your body thinks from a cardiovascular standpoint that it's back on the ground. I was in the bag for 5 hours on the day before landing, taking salt tablets and drinking water, trying to force fluids into my body, and we think it's a very effective countermeasure preparing us to come back. John, Shannon, and I also participated in an experiment, which you can see John connecting here, which measured our blood pressure and heart rate throughout the entry and landing phases.
After 2 weeks in orbit with a microgravity research laboratory, we reconverted the laboratory back to a spaceship, and here we are on entry day, Mach 17, 200,000 feet. You could see the flames out the front window. We're in the middle of a fireball during re-entry. And Dave took this photography around the flight deck, and so you can get some idea of what we're doing on board during that time frame. Here the vehicle is subsonic now. We're rolled out on final, aimed about a mile short of the runway to do the landing task. What a beautiful flying machine. back into the cockpit. Dave took this as we're in the flare, and then Rick's putting the gear down here. Bill's calling out the MLS accuracy, and we're going to land the spaceship. And the vehicle touches down here at about 230 miles per hour. As I derotate, Rick puts the drag chute out, and we roll on out. And I'll just tell you the bottom line of this space shuttle mission. It was a tremendous success, and medical researchers will learn more about human physiology as a result of all of this data, and therefore will enhance their ability to cure illnesses that plague people here on planet Earth.